I'm Ryan Tibshirani. Larry Wasserman, your usual instructor, is currently living it up in San Diego in a beach house hotel. And I'm here giving you guys his guest lecture. So Larry asked me to talk about trend filtering. I think you guys covered non-parametric regression last week. Is that right? So throughout, I'll probably be asking you what exactly you covered, because I'm not sure. I couldn't really tell from his notes as to whether you actually went through all of that in detail. Looked like a lot. And to get to trend filtering, to have you kind of appreciate the beauty of trend filtering, I decided that it's probably worth stepping through a bunch of kind of important topics that relate to it. So we're going to start off by just reviewing splines. You guys learned splines, is that right? Could you nod your head noticeably if you learned splines? Oh, so you didn't learn splines at all. Larry didn't cover them at all? Briefly. OK. So I'll give you an introduction to splines. Then we'll talk about smoothing splines. And then we'll get to what I call the limitations of linear smoothers. You talked about what a linear smoother is, right? And then we're going to get to three nonlinear smoothers. These two are probably the most famous nonlinear smoothers, wavelets and locally adaptive regression splines. And the last one I'll talk about is trend filtering, which is a more recent nonlinear smoother. And then if we have time, we can talk about some extensions. I'm not sure that we'll have time for that. But there are a number of things we could talk about, like additive models with nonlinear smoothers, higher dimensional smoothing, smoothing over graphs. We could maybe just pick one of those topics and talk about it a little bit. So far, all of this is going to be in the univariate setting. Okay, so everything that we talk about all the way through trend filtering, we're just talking about usual kind of classical univariate function estimation. As I hope Larry taught, anytime you have a univariate smoother that you like, you can always apply it in an additive model. Okay, so even if I didn't get here, and all you learned was about all these kind of more complicated but effective nonlinear smoothers, you could immediately apply them in an additive model to do high-dimensional non-parametric estimation. Okay, you wouldn't really need to have another class in that. You could just plug them into an additive model, because an additive model is built out of univariate components. Okay, so if we have more time, I may talk a bit more about kind of some extensions. All right, so our data model for most of this, in fact, all of this except the extensions, is going to be the following. So we're going to think about observations and inputs, so yi and xi, that are related by the following regression equation, where f0 is some unknown regression function. And these are errors that we observe when we observe these observations. Okay? Or sorry, these are errors that are made when we observe these yi's. Okay? And as Larry, I think, taught, you can always kind of write a relationship between yi and xi in this form, where epsilon I has mean 0, just by taking f0 to be the conditional mean of y given x. If you defined f0 to be the conditional mean of y given x, then I would be able just to write epsilon I as the residual in this equation, and it would have mean 0. Okay, so there's no loss of generality in writing down this data model. What are the types of functions we're going to be thinking about today? We're going to be thinking about smooth functions, and we're going to define that specifically with respect to some class. Okay, so we'll kind of have different classes in mind for the different methods, and I'll make that clear. But think about f0 being in some class script f of smooth functions. And lastly, for the inputs, or the predictors, we're going to think about them as fixed today. So we're going to think about xi as being fixed or as random, but independent of the errors. Now, I know if Larry was here, he would give me a disgusted look. Larry and I differ on this perspective. I think it's much easier to teach regression with fixed inputs or with random inputs that are independent of the errors. In fact, a lot of the theory is more precise in that case, and some of the stuff you can say is cleaner. Of course, in practice, I think that it's probably unrealistic to think that whatever the errors that are made in this equation are independent of the inputs. Okay, because of omitted variable bias. That's one thing that you might learn in even a linear regression class. Like maybe 705 would have talked about that. But it's not, it's actually fruitful to make this assumption in terms of understanding what's going on at a basic level, so we're going to assume that today. Okay, so that's the basic data model. Is there any questions before we start? Because this is kind of like the jumping point for all the good stuff. Okay, so I'm going to try to keep this board for some of the takeaways. So I'm going to kind of write maybe some key things up on this board every once in a while about the methods we learn. And I'm going to try to use the two right boards just for most of the development. So we can refer back to that board later. So let's talk about splines. So splines are simply piecewise polynomial functions. So let's specifically think of a spline of degree, say, k, with knots at some locations, say, t1 through tm. Okay, so what is a spline of degree k with knots at some locations t1 through tm? These are just numbers. That is specifically a piecewise polynomial of degree k with knots at these locations. Okay, so if I were to draw it, suppose I've ordered these knots, t1 through tm. Again, we're just thinking about univariate functions for now, or like I said, pretty much exclusively. Okay, so a degree k spline just is a polynomial in each of these intervals. It can be a separate polynomial of degree k. Right, so it could just do something in each of these intervals. But what makes a spline very special over just a pure piecewise polynomial is it has an extra set of conditions, which is that actually all of the lower order derivatives, so derivatives of orders 1 all the way through k minus 1, including the 0th order derivative, so the function itself, these are all continuous at the knot points. Okay, so it's a very smooth piecewise polynomial. Okay, so I can't have the function being discontinuous across these knot points. Its derivative can't be discontinuous. Its second derivative can't be discontinuous, all the way up through its k minus first derivative. So it's a very smooth piecewise polynomial. Okay, so such that, so let's just call this f. F itself, f prime, f double prime, all the way up through f k minus 1. This is the k minus first derivative. These are all continuous functions. Okay, so why do we like splines? I claim that splines play a very central role in nonparametric estimation and statistics. They're also very central in applied math. There's a ton of work on approximation theory using splines and numerical analysis. They're used a lot in computer graphics. So they're kind of ubiquitous. And there's whole books on splines. So why do I like splines so much? It's because they're very expressive. So if I put enough knots down, I can represent very kind of a very rich class of functions. Right? They can kind of take fairly arbitrary shapes, but they're simultaneously very smooth. So if I didn't have the restrictions that the function was continuous at, or its first derivative, say, was continuous at the knots, then if I estimate a spline from data, I make it kind of weird effects at the boundaries. Right? I may end up being misled by some boundary point and get something like that. And in terms of the bias variance trade-off, I may be expending variance for no reason. Right? If I restrict the class of the things I'm looking at even further by saying, no, I actually want this to have a smooth derivative at the knot point, then essentially I may be increasing the bias because I'm not allowed to look at as many functions. But I'm increasing the bias at the cost of reducing the variance. Okay, I'm not allowing the function to take kind of arbitrary shapes at these knot points. It has to be very smooth. So at a very high level, we think that splines are good because yeah, even though they maybe increase the bias versus if I just looked at all piecewise polynomials, they reduce the variance substantially. And we're going to actually see maybe not so informal but not so formal at the same time description of just how complex splines are when we look at the dimension of the space of splines with given knots. So you're going to see that actually they don't really, their complexity is quite controlled. So that's a spline. And now how do we use splines? Well, the very first thing that you might do to estimate a spline from data is just to fit what's called a regression spline. So you're given these pairs, right, xi, yi, come from that model, that data model that I wrote up there. And you're going to choose some degree. So if I chose, for example, k equals 1, or let's suppose I chose k equals 3. It's probably the most common case. These are piecewise cubic polynomials, so they're very flexible in between the knots. And it's called a cubic spline. So it's a common choice. For example, just choose 3. And choose a set of knot points. OK, so this one you should look at and say, oh, I could probably do that given data. It's not a big deal. This one you should probably look at and say, that's much more suspicious. How do I choose knot points? So we'll address that shortly. So I just choose some knot points, say t1 through tm, between the range of the observed x's. OK, so I just fix a bunch of knots. And then I'm going to think about estimating a regression function. So I'm going to parameterize the functions that we're going to be using to estimate the relationship between y and x in the following form. I'm going to model it to be a sum of m plus k plus 1 functions. So m is the number of knots. K was the degree of the spline. And these functions form a basis for splines. So these form a basis for splines of degree k with knots at these values t1 through tm. So in other words, if I were to look at all possible choices of coefficients here, these functions have the property that I can express any spline of degree k with knots at t1 through tm as such a linear combination. That's what a basis means. Right? A basis for a function space, or a basis even for a vector space, it's the same analogy. It means that linear combinations of those elements give rise to all possible members of whatever the family is you're looking at. So here it's splines. Okay. It's a fair question. So I'm going to write down the basis for you, and then I'll maybe leave it as an exercise, or you can look at. Actually, I totally forgot. Sorry about that. This is kind of high. I put the notes for this lecture online. Thank you for reminding me. So anything I say here, there's more detail in the notes that I put online. I think it's just called SML notes.pdf. OK, so let me just say one thing about this. These were notes from the sequence of lectures on non-parametric regression that I gave for this course last year. So it contains a lot more than just this, but you can certainly look through it and find these topics. So in other words, I don't think I don't think Larry's going to expect you to know everything that's in his notes. I think just the relevant parts on splines and in this stuff is in these notes. And the same link, but then talk.pdf. I put in a talk on trend filtering that I've given a few times recently that is maybe just more pictures, more color pictures in the notes. And it doesn't cover all of this stuff, but at least it covers trend filtering. So this one may be, more fun to look at than just a set of notes. Okay, so like I said, anything that you see and didn't manage to write down or didn't manage to fully digest, you can certainly take a look at those two links. So, okay, so the question was, why do I only have to write down m plus k plus 1 functions? Yeah?
I think you're missing relatives between this and
Oh, yes. Thank you, Jisoo. I don't own all of stat.cmu.edu. It's true. So in here should go tilde and then my username. Okay. So I'm going to actually tell you what such a basis is. You can choose many different, ways to express this basis. There's not a unique way to express this basis. Just like there's not a unique way to express a basis for a vector space. I can always choose different linearly independent vectors that span the space. But there's one that's, I think, particularly helpful to think about, and that's the truncated power basis. So we're leading up to a practical method just a few minutes away. Practical method for fitting regression splines. And we're going to use something called the truncated power basis. And what this basis looks like is that the first k plus 1 functions in this basis are just polynomial functions, the kind of canonical polynomial functions of x. So if I just included these functions, then I'm saying I'm going to model f as a polynomial function of x. So it'd be like doing polynomial regression rather than linear regression, right, in one dimension. But we're going to go beyond that. We're going to include not only these functions in our basis, we're also going to include what you might call the not producing functions. So these ones aren't piecewise polynomials, they're just polynomials, right? We're actually going to go beyond that and include these functions. So for all j going between 1 and m. So this notation means I take x, I compare it to the jth naught, and I take the positive part, which means that if x is smaller than tj, I just set this to 0. If x is bigger than tj, then I just get x minus tj, and then I raise that to the power of k. So let's draw these functions, these functions. So these functions, you know what they look like, just polynomials. Let's draw these functions. So if I were to look at t1 all the way through tm, right, then say this first function, it's 0 before t1. And then after t1, it just looks like x minus t1 to the power of k. So it's a kth order polynomial that rises smoothly from 0. And you can check, just do some elementary calculus, that this thing actually does have a smooth first derivative, second derivative, all the way through k minus first derivative at t1. Okay, so it is indeed a spline. So this is what my basis looks like this. This is what gives me knots. So this is what allows the polynomial to change in between the knot points, t1 and t2. Right? Because if I were to add these together, then basically I can get a different polynomial contribution in each interval, okay, plus some overall polynomial trend. Okay, so it's a kind of standard fact for people who study splines. Maybe it's like the first homework problem they do, that this thing actually.
Instead of the k plus 1 be x to the power of k instead of to the power of k plus 1.
This one?
Yeah.
Thank you. Yeah. Right. So it's kind of a standard homework problem for a class on numerical analysis or something that studies splines to prove that this actually spans the space of splines of degree k with knots at these points. So I'll let you guys think about that. I think maybe the notes have a few pointers as well. In other words, if you give me any spline whatsoever, I can always represent it as a linear combination of these functions, as long as that spline has degree k and knots at these points. So in other words, the proof that I only need n plus k plus 1 of them, whoever asked that, is constructive. So here's the proof. It's these things actually, well, I guess you have to prove these span the space, but at least I'm giving you a big part of that, right? I claim that these are actually a specific basis, and there's only n plus k plus 1 of them. OK, so now let's get practical. So let's go back to regression splines. So first step is that I choose k, choose the knots. I parameterize f according to that form, where those are the truncated power basis functions. So I just evaluate those basis functions basically at all of my knot points. Right? That's just some computation I have to do in whatever my favorite programming language is. And then I'm going to solve just a kind of standard least squares regression of y on these basis functions in order to determine the coefficients. So I'm going to actually solve this problem, minimize over all choices of coefficients theta, the sum of yi minus theta j times gj of xi squared. OK? And whatever solves that problem, I'll call theta hat. And that's going to give me this function called f hat. That's my regression spline. OK, just take the coefficients that minimize this. OK, so hopefully that is kind of familiar, at least from the perspective of linear regression or just least squares regression. And I can rewrite this, right? I can rewrite this problem in the following way. Minimize. I'm going to use kind of more condensed notation. Just the L2 norm between the vector y of observation. So this vector just has components y1 through yn. And this is going to give my coefficients vector theta. So it contains theta j along its components. And this is my basis matrix G. OK, and G is going to specifically have elements that look like this. OK, so these I claim I just set up G according to this expression. So the columns of G contain the evaluations of a particular basis function, Gj over across all the predictor values, xi. Then these are the same thing. I've just rewritten it in a little different notation. I'm taking linear combinations of the columns of G, the same thing as doing G times theta. And this is the same thing as I expand out as just y. And so, of course, from our favorite expression, we can write down an analytic form for theta. Right? It's just G transpose G inverse G transpose y. So those are the coefficients. So really in software, all I need to do is populate this basis matrix and then solve this linear system. And the fitted values, so the estimates f hat at the points xi, which we denote by y hat. So these are what I estimate the regression function to be at the input points. They're just given by g times theta hat. Right? That's exactly this, just evaluated at all the points x1 through xn. And this is just a linear function of y. Okay, it's just some linear transformation times y. So this is what Larry called and what is commonly called a specific type of linear smoother. Okay, so not to be confused with the linear function of x, nothing to do with that. Right? I could have done this and then fit this particular function to regression with a regression spline just by putting down a bunch of knots. But the point is that the fitted values, thought of as a vector, y hat, they are given by just some matrix times y. That matrix only depends on x, doesn't depend on y. Okay, it's a linear smoother. All right, questions about regression splines? Hopefully that's clear. Okay.
Is there intuition towards the dimension of the degree of freedom? There's a plus one there. So k plus m plus one. What is the intuition for the plus one?
Plus one. So the space of polynomial functions of degree k is of dimension k plus one, right? Because those are the functions that span it. And then you just get one basically dimension or degree of freedom for every function that gives you a knot. Yeah?
What about high-dimensional splines?
High-dimensional splines. So, I mentioned that kind of you can always fit additive functions. So I could always do this along each dimension, right? I could model, if I had, say, d variables, I could model y as a spline function of x1 plus a spline function of x2 plus a spline function of x3, etc. So that would give me a spline that essentially decomposes according to the coordinate axes. That's usually the way that people approach high-dimensional estimation. But in lower dimensions, like 2 or 3, there are kind of more rich extensions of splines. So thin plate splines is one example. Tensor product splines is another. And those are in the notes. You can look at that link. Okay, but you usually don't fit like a full spline to dimensions more than, say, 3. Usually just do an additive function of univariate splines. Okay, so there's something that is kind of unsatisfying about this construction, and that's the following. We have to choose the knots. Okay, so choosing the knots in practice is there's not really a very principled way to do so, and whatever we choose can affect our final answer, and so this is not really something we want to have as a prescription, as a step in our prescription, right, to fitting splines. So people, first of all, splines are very old. Splines, I think, date back to at least the early 1900s, and people had thought about splines in statistics as early as, say, the 1930s and 40s, and so through, say, the maybe 50s, 60s, 70s, 80s, people thought about choosing knots. So how do I choose knots? And they have all sorts of greedy selection procedures, like I'll pick a knot somewhere that looks the best, and I'll pick another knot that looks second best, and et cetera, and I'll keep fitting the spline and adding more knots as I think I need them. These things were popular for a while, but they're actually not, they're still kind of heuristic. We don't really know, if they work well in full generality. And then there was a technology that came out that I think was very, very important in statistics, and pretty much everybody uses it now to fit splines, at least splines that maybe are of the classic form, and that's the smoothing spline technology. So smoothing splines came out. So smoothing splines were studied as early as 1960, but it wasn't until Grace Waba and other people who kind of really championed for them that they became popular, and that was more, I think, around maybe the late 80s. So some of the most important papers on splines come from the 80s and 90s on smoothing splines. So smoothing splines are this very beautiful idea that allow us to fit flexible splines with knots at every data point, but in a way that's not overfitting. So before we get there, let's just pause for a second, and let's try to think about what the problem would be if I just chose these t points to be all of my x points. Why would that not work?
Like a p greater than n problem?
Yeah, right. So I would have n plus k plus 1 basis functions, and I have n points. So first of all, this wouldn't really even be well defined. Right? The thetas here would not be unique. It's like a p greater than n problem. So the number of columns of G, which we can think of as maybe the dimension, which is usually referred to as p in regression, is more than the number of rows. So that's one problem. What if I even just chose, say, n minus k minus 1 of my points, x1 through xn, to be the knots, so that my total number of degrees of freedom was still n? What would be the problem there? So I suppose I threw out the smallest k plus 1 points, and the rest of them I just chose as my knots. So the number of basis functions is still n. What would I get from this problem? What would the fitted values be, for example?
Fit exactly.
Exactly, right. So they would fit the y's exactly. I just would be interpolating the data. So it would be totally useless. That's because that would make G have an n-dimensional column space, so I could always find a theta that made g theta exactly equal to y. Okay, so that's not really an answer at all that we can deal with regression splines. We can't just kind of trivially choose a large number of knots. Even if the number of knots we chose was close to the number of data points, we would still probably not believe that this was a very good estimate just because there's so much flexibility. So smoothing splines do something which is very clever, which is that they choose all the data points as knots, but then they regularize the function so that it has so its derivatives are kind of under control. So let me first pose to you the cubic smoothing spline problem, and then we'll kind of spend a bit of time talking about it. So the cubic smoothing spline problem is actually not posed in a way that initially at all looks like this. So we don't write down the coefficients that we solve for, and we don't write down basis functions. It's actually posed as a very general mathematical problem. And this is where it kind of developed a lot of interest in math as well, which is a minimization problem over functions. So I'm just going to look at all functions f. I'm going to be trying to minimize the squared error between my input points xi and my observations yi. And of course, if that wasn't my only part of the criterion, then I would just choose f again to interpolate the points. So this would not be useful. But then smoothing splines add this second part, which is a roughness penalty or a complexity penalty on the function f, which is I look at the second derivative of f, I square it, and I integrate it across the entire domain of the x's, and I use that as a penalty. So this says that if f has a second derivative that changes a lot, or let's say if f's first derivative changes a lot, then we're going to incur a large penalty. Okay, so it tries to encourage the second derivative to be small, basically, throughout the entire domain of the x points. Okay, and this lambda is called a tuning parameter. So the larger I make lambda, the more smooth my function is. The smaller I make lambda, the less smooth my function is. What happens if I took lambda to be infinity? What would I get out of this problem? So I took lambda to be larger and larger and larger. What kind of functions have 0 second derivative, right? Because if I took lambda to be larger and larger and larger, then we put all of our weight on minimizing this term. So we make the second derivative 0 everywhere. And what kind of function would that be? It's a linear function. And so among the class of linear functions, what function fits the data points best? Just the linear regression fit. So if I take lambda to be infinity, I get as a special case of this just the straight line that I get from the linear regression fit. As I take lambda smaller and smaller and smaller, I get something more smooth. Okay, so this is an infinite dimensional minimization problem because we don't have coefficients like theta, j that we're trying to solve for. We're trying to look at all functions. So essentially, it's impossible to solve this problem in general, right? I mean, it's impossible to solve functional minimization problems in full generality. If I just gave you an arbitrary criterion here, there aren't algorithms that we have for solving these kinds of problems. But this is a very special functional minimization problem because it has a finite dimensional subspace in which the solution always lies. So this is a very famous result for smoothing splines. And the result is as follows. I'll just attribute it to Grace Waba. But I'm almost 100%. I'm more than, I was going to say more than 100% certain. I guess you can't be. I'm 100% certain that people had done this earlier than she did, but this is a very famous reference, so I'll just put her name there. The theorem is that the solution to the above problem is always a cubic spline with knots at the data points. So I'm just going to assume that these guys are ordered just for simplicity, right, without any loss of generality. Okay, there's actually a unique solution to this problem for any value of lambda that's positive, and that's a cubic spline with knots at the data points. Okay, it's a very beautiful result. And the proof of that is actually in the notes that I put up there. It's just integration by parts. It's about half a page long. So it's a very elegant proof as well. Okay, so in other words, it tells us that if we're looking at all functions, that kind of trade off complexity in this way with fits to the data in this way, then we don't need to look any farther than cubic splines, because they're going to be basically the best we can get. There's one caveat, and that's that actually this is a natural spline. It's a natural cubic spline is just a spline that has the additional restriction that before x1, so to the left of x1, and after xn, so to the right of xn, the function is linear. It's not even cubic. So remember, in between these knot points in the inner intervals, I'll just draw you a picture. Cubic splines are just cubic polynomials, right? So it looks something like this. Natural cubic splines just have the additional restriction that actually they're just linear beyond the boundaries. Okay, so they're even more restricted than splines. And that's actually a desirable property, because if we don't have data out here, we don't want something complicated happening, right? A linear function is probably better than a cubic function. So that's a natural cubic spline. And this is what sometimes people call a variational result for smoothing splines. So it takes this infinite dimensional problem and it turns it into a finite dimensional one. So why is this finite dimensional? It's exactly kind of for this reason we had up here, which is that once I know this is true, I can just write down a basis for splines with knots at the data points, and then solve for and then plug in this parameterization, right, wherever we wrote it down. F equals the sum of theta j gj. Right now we actually have a lot more gj's. I have n gj's. And I just solve for the coefficients theta after I plug in that parameterization for f in this problem. So let's go ahead and do that so we can see what the finite dimensional problem looks like for splines. Okay, so here, instead of having just m plus k plus 1 knots, we actually have how many knots? You might think it's n plus k plus 1, because I actually have, sorry, how many functions are there, right? What's the dimension of the space of splines with knots at those points, x1 through xn? And here actually k is, what is k? K is 3 here. So we might think it's n plus 4, n plus k plus 1. But for reasons that are not difficult to explain, but I don't really want to spend the time going through them, natural cubic splines actually have even less degrees of freedom than splines. You can see why that's true, because they're only linear out here, they're not cubic. And that they have this beautiful property that no matter it's actually true no matter what the order is. If you have a natural spline of order k with knots at n points, the dimension of that function space is n. It doesn't even depend on the order. Okay, so we only have n basis functions here. Okay, this just comes from the fact that we have this natural spline restriction. Okay, so it's a neat fact about natural splines of any degree. And there's some details in the notes, but I think it's probably not worth us going through them. Okay, so in other words, you can just think about, for reasons that maybe aren't so important, this particular finite dimensional function space only has dimension n. And I can again write down a basis for it. It looks like the truncated power basis. And so I can program that up in software. And all I have to do now is solve for these coefficients theta. So then the problem ends up being equivalent to, so let's call this problem star. This problem star is equivalent to minimizing over all theta just very similar expression to what we had before. Just plugged in basically for f in that first term, plus lambda, our tuning parameter, times the integral of the second derivative of f squared. So what happens when I take the second derivative of this function? I can just move it through, right? So I get the sum of theta j times gj double prime x, this whole quantity squared, and then integrated over all x. So that's the problem we need to solve. And our parameters are theta. Those are the coefficients we need to solve for. Okay, and as before, for the exact same reasons as for regression, as I had with regression splines, I can express this more concisely, at least the first term more concisely like this, where that G is what I would call the basis matrix. So has entries Gij, which is equal to the jth basis function evaluated at xi, plus lambda times, I want to express this thing in matrix form to get it kind of on the same level as that first term. Because it's just easier to deal with these problems when we think of them as kind of more abstract minimization problems in vectors and matrices. So let's just look at this kind of for a second, and don't worry about the details. And let's try to guess what kind of function of theta this is going to be. If I wrote it as a what kind of function of theta is that going to be? If I wrote it as just in terms of vectors and matrices. Quadratic, that's exactly right. So how do I see that? Just move the square in, okay, and write this as the sum over all j and l of theta j times theta l times gj double prime times gl double prime. And I see that I have products of theta j and theta l for all j and l. And in fact, with the appropriate definition of a matrix omega, you can see it's exactly of this form. Theta transpose omega times theta. This omega is just going to contain the pairwise products, right? Gj double prime times gl double prime. Integrated, so that you can pull the thetas outside of the integral, right? Because they don't depend on x. Okay, so with some appropriate definition for omega, right? And again, these are all things you can do kind of offline. You give me the x points, I'll populate g, I'll populate omega, just according to my basis functions and some simple linear algebra calculations. And then I can solve this problem, right, in the finite dimensional parameter theta. And this is like a generalized ridge regression. If you guys took ridge regression, this is just like ridge regression, except for I have actually, instead of the L2 norm of theta squared, it's actually kind of like the L2 norm but on a different basis. It's theta transpose omega times theta. And the solution you can get just by differentiating and setting equal to 0 is exactly equal to the following. It's still just a linear function of y. So, at this point, this stuff maybe looks routine, and I think, when you type in smooth.spline in R, it does this for you. The MATLAB has a smooth spline function. I can't remember what it's called. I know Python does as well. But if we step back for a second and think about it, this is really remarkable because through very simple kind of linear algebra calculations, we've solved an infinite dimensional minimization problem. We've actually solved this problem. Right? So after I have these thetas, I just take f hat to be the sum of theta j hat gj, and that actually solves that original problem. Okay, so this was a huge kind of advance in spline usage, even practical spline usage. Now smoothing splines are ubiquitous. People use them a ton for smoothing. I would claim even more so than kernels, although Larry would disagree with me probably. And the reason why we like them is because we don't have to choose knots. All we have to do is choose a single parameter. This parameter is called lambda, and it controls how smooth we want the function to be. If I make lambda larger, the function is overall smoother. If I make lambda smaller, the function is overall more wiggly. It's much easier to choose that, say by cross-validation, than it is to choose knots. There's many more things to choose. Questions about smoothing splines? Yeah?
What do the basis functions look like?
The basis functions here, they look like the truncated power basis functions, essentially the same. But the only difference is that I claim these were actually natural splines rather than splines. So you get them from taking very simple combinations of truncated power basis functions. I think that's also in the notes. Basically, we have to just be careful that beyond the first and last points, it's linear. So we have to somehow cancel out any cubics that happen after these points. And that's just done through kind of simple subtraction of truncated power basis functions.
Those basis functions are all of order k. I mean, you have only one term in each function.
I don't quite understand the question, sorry.
I mean, if we, because you write earlier, there's a truncated power basis function, and they only have one term in each function.
One term. So they're just univariate functions. Is that what you mean?
Oh, they're just they subtracted the.
We subtract different. Basically, the natural spline basis is gotten by taking different combinations of truncated power basis functions, just in a way that cancels out this behavior beyond the boundaries.
Larry said this is a kind of reproducing kernel Hilbert space. Is this method has some similarity to the method of that?
Yeah, good question. So indeed, smoothing splines are a special case of RKHS estimates, and that wasn't seen until well after they were kind of developed and studied. That came later, but Grace Waba is one of the first people to have identified that. And some people say that if Grace Waba got together with, Vapnik or something in the 90s, then all this stuff would have been done. We would have kind of figured out all this stuff much earlier, because she was also working on RKHS stuff, but just in statistics, not in computer science. But to be honest, I don't like the way to think about them. I don't like to think about them in terms of RKHS estimates, because the kernel Hilbert space itself is very odd. So the kernel you choose to get smoothing splines is a very odd one. It's called I think it's called a log radial basis function. So it's not one that you would usually choose just on first principles. Okay, so this is maybe the easier way to think about it. But this is, you're right, a special case of RKHS, an RKHS smoother, a smoothing spline.
Continuing with that, so then this theorem here would be the special case of the representative.
Exactly. Yeah. So this theorem is a special case of the representative theorem for RKHS estimates, which sometimes people call Mercer's theorem.
And this form is the Mercer expansion of that kernel?
No, because the Mercer expansion is usually infinite, right, in terms of the eigenfunctions of the kernel. So this is using the kernels of representation. Yeah, if you're comfortable with RKHS, you can think of all this stuff in this framework. Although I think the proofs and the derivations for smoothing splines are just more kind of self-contained, right? So this proof is just integration by parts. It's like maybe 4 or 5 lines long. So it doesn't involve as much kind of functional analysis as is required to understand RKHS stuff. But there's more in the notes if you're interested in that connection. All good questions. So I want to say a few more things about smoothing splines, and then I wanted to actually depart from them. When does this class end? I actually have no idea. I'm sorry. Is it 2:50? Okay, so we have a lot more to cover. I think I'm going to probably just tell you why smoothing splines suck. Really, I just told you why they're so great, and I'm going to tell you why they're so terrible. So we can move on to the nonlinear smoothers. But I'll just say 2 things about them really quick before I tell you why they're not great. Okay, I'm going to just keep this last equation here. Okay. So this last equation shows us that actually y hat is just some linear function. We'll just call it s times y. I just get that by multiplying, right? Y hat is just g times theta hat. So it's a linear function of y. S is just g times all this stuff. So it is, again, a linear smoother. Now this matrix S depends on the x points. It also depends on lambda. But modulo, if you've chosen lambda, so modulo choosing lambda, that's just a linear function. It doesn't depend on y. It's a linear smoother. So it's the same. It's in the same class as smoothing kernels, RKHS estimates, smoothing splines, and many other things you probably haven't learned about as well are all linear smoothers. So there's a very, very big class of estimates called linear smoothers. And I'm going to try to tell you in just a few minutes the limitations of linear smoothers and why people kind of after smoothing splines turn to nonlinear smoothers. But a few important things first. So I'm going to just claim that with the proper choice of basis, so if instead of using the truncated power basis, I use something called the B-spline basis, and B-splines specifically are what gets used a lot in computer vision, then so it's just a different way of spanning the space of splines, and it's harder to understand than truncated power basis functions, so that's why I didn't define them for you guys. This computation, so yeah, this linear system, so the linear system that defines theta hat can be solved in order n operations. So actually, smoothing splines are extremely efficient. Okay, it's because the B-spline basis actually makes this matrix banded. So B-splines have local support, unlike the truncated power basis. And because they have local support, you can actually prove this matrix is banded, which means we're solving a banded linear system to get theta hat, and that can be done in order n operations. And people actually have gone even farther than this and proved that for cubic splines, it's about 32n. So that's the constant. People have all sorts of very, very efficient specialized algorithms for smoothing splines. Okay, so an advantage of smoothing splines is that they're very, very efficient. You can fit them on very large problems very efficiently. That's why they're also used, like I said, in applications like computer vision, where maybe you're doing large problems. You're doing smoothing in large problems. In computer vision, actually, it's usually beyond univariate. It's like a 2- or 3-dimensional spline, either a thin plate spline or a tensor product spline. So that's one nice property of splines, and the other of smoothing splines. The other nice property is their statistical property. So that's computational. This one is statistical, and this comes from Sarah Van de Geer in 1990. And we're going to try to pit this against nonlinear smoothers, what nonlinear smoothers can do. So let's see if I can remember exactly the function space. So first, I'm going to actually change this to m. So let's think about taking an arbitrary number of derivatives. So m was 2 for us before. And instead of a cubic spline, we now get a kth degree spline, where k is equal to 2 times m minus 1. So this is the more general form of the smoothing spline problem. If I took 3 derivatives, if m was 3, then I'd get a quintic smoothing spline, so a 5th degree piecewise polynomial. Okay, let's just check that we got back the right orders for m equals 2. If m equals 2, then k is equal to 4 minus 1, which is 3. It's again a cubic spline. So this is just the more general form of the smoothing spline problem. So what Sarah Van de Geer proved is that if our true function, f0, is in a particular function space, which we're going to call a w of m of a constant c, this is called the space of Sobolev functions. Did you guys study these function spaces? So did you guys learn what this one was? Oh, great. So now you can see why these function spaces are important. So just real quick, this just means it's the space of all functions have the property that if I take m derivatives, I square it, integrate it, then that's less than or equal to c. So she proved that if f0 is in the Sobolev space, so it means the true function we're trying to estimate has m derivatives, and its complexity, according to this measure, is bounded by c, where c is a constant. Then if I choose lambda to be something on the order of n to the 1 over 2m plus 1. So I choose lambda to grow bigger, but grow bigger very small at a very slow rate. So as I get more data, I'm increasing my penalty on complexity, but at a very slow rate. So n to this power of 1 over 2m plus 1. Then with this choice of lambda, so then for I get the following property, that in say whatever metric you like, so let's write this as the norm squared. So the norm between f hat and f0. Now these are functions, so you could take it to be whatever metric you like. You could take this to be the integral L2 norm. So that means I take f hat of x minus f0 of x. I square that and integrate that. That's one way to do it. You could also think of that as this in terms of an empirical version. Okay, I could do something like the average square difference between f of xi and f0 of xi at my data points. Those are both two valid choices for this norm. So this is just some way of looking at the distance between f hat and f0. Then this is less than or equal to some other constant, c prime, times n to the power of minus 2m over 2m plus 1. So these are maybe kind of similar to rates that you saw with Larry when he derived rates for kernels and stuff. Okay, so it means that if we assume that the function we're trying to estimate is smoother and smoother, then we get a faster and faster convergence rate to our true function f0. So we're estimating it better and better. And this kind of rate is optimal. That's the other nice part about this. This is optimal over this function class. F0 is the regression function, so it's according to our model up there. F hat is the smoothing spline solution. Get for F hat smoothing spline estimate this property. Okay? Okay, so the details aren't super important, but I wanted to give you a statement of why smoothing splines are they're powerful tools statistically. And the thing to remember is that there is some function space, it's the Sobolev space, over which smoothing splines are optimal. They do the best you can do in terms of estimation. So this means, and you'll learn this precisely when you study minimax theory later in the semester, I think, that if you looked at basically any estimator, smoothing splines, kernels, whatever you wanted to, for estimating functions that are in this class, you couldn't do better than this rate. So this is the best rate you can get. Yeah, Hannah.
Is the plus one only valid for one-dimensional problem?
Right. So this would be D if this is a d-dimensional function space. Okay, good question. So there's an analogous result for higher dimensional function spaces. We're just looking at univariate functions for now. All right. So I'm sorry that I'm going to be moving through this quickly, but I do really want to get to nonlinear smoothers. So I've so far told you why smoothing splines are great. They're computationally efficient. They don't need us to choose knots. And they're optimal over the Sobolev space of functions, which is actually a very, very common function space for non-parametric estimation that people consider. So you probably considered the Holder space when you studied kernel functions. They're basically the same thing. So Holder space, Sobolev space, they're actually even formally like basically the same function space. So what's wrong with them? Why are we even going any further? Why don't we just quit class early and enjoy the rest of the 20 minutes? It's because smoothing splines, but not only smoothing splines, any linear smoother, so kernels, RKHS estimates, any linear smoother, they cannot estimate a certain type of function very well that lies outside of this function class Sobolev spaces that actually is quite common to encounter in practice. And that's the limitation of linear smoothers. So let's get to that now. All right, so linear smoothers, limitations of linear smoothers. So there's two ways to look at this. One is practical and one is theoretical, and we're going to kind of go through both. The practical one is quite easy to explain. Suppose that I gave you data around a regression function that looked like this. Okay, so I'm trying to estimate some function. Maybe this is like the mean level of the stock over some period of time or something, and the function is smooth at some parts of its domain, but then it just abruptly becomes non-smooth. And at any parts of its domain, it could either be smooth or non-smooth. It has a mixed degree of smoothness. So functions that have mixed degrees of smoothness, these are actually called heterogeneous functions. So in other words, we call them heterogeneous functions. I could also have the function being smooth, and then there's just a big spike. It's another heterogeneous function. Okay, so this might be something like you might be observing some neural activity over time, and the person's neural activity is pretty constant, and all of a sudden you scare them, you yell in their ear or something, and you see a spike. Right, so these functions, smooth functions, we shouldn't fool ourselves that every function we try to estimate is like uniformly smooth. That's not going to happen in practice, in many practical situations. So mixed degree of smoothness functions i.e. heterogeneous functions, heterogeneous smoothness. And this is not a mathematical statement. It's just trying to emphasize a point. This is like kryptonite for linear smoothers. Okay, so they just can't handle functions of mixed degrees of smoothness. And so you can see a nice example in the notes where I have a function that looks like this. And if you try to fit it with a linear smoother, say smoothing splines, then no matter how you tune lambda, it's just not going to pick up this behavior. Okay, so with a smoothing spline, if you make lambda large, it's going to do a good job of smoothing this out. Then it's going to try to smooth this out as well. Okay, if you make lambda small, so you say, okay, I want the function to be more complex, then it does a good job of picking this up, but then it actually kind of undersmooths the rest of the function. Okay, so no matter how you choose lambda, for mixed degrees of smoothness, smoothing splines, but linear smooths in general, cannot represent those types of functions. That's the practical reason that we don't like linear smoothers. And this is a Blackboard lecture, but you can take a look at the examples in the notes or many other examples and some of the links I sent to just see a bunch of practical examples where linear smoothers cannot represent heterogeneous functions. So there was a very influential paper in 1998 by Donahoe and Johnstone that made this kind of notion very precise. And that's the theoretical reason that we don't like linear smoothers. So I'm going to summarize that for you. I'm going to skip wavelets, I think. We just don't have time for them. And I'm going to super quick introduce to you trend filtering and locally adaptive regression splines, two very closely related nonlinear smoothers. So let's get to the theoretical statement and then those two estimators which kind of solve the conundrum of estimating heterogeneous functions. All right, so there's this theorem by Donahoe and Johnstone. So before I give you the theorem, I'm going to draw for you a picture. Okay, so let's think of two function spaces. This function space, let's suppose, is the Sobolev space of order m plus 1. So it's the functions that have m plus 1 derivatives, and whose m plus first derivative, if I square and integrate it, is less than a constant. Let's just call that constant C. Okay, turns out that that function space I can actually embed in a larger function space. And that is the, I guess I'll call it script T, order m, of a different constant, C prime. So there's a constant C prime in a function space Tm of C prime that contains this space. And in fact, the relationship is just C prime is C plus 1. And this function space is called the total variation space rather than the Sobolev space. And it's equal to the set of all functions, f, such that the total variation of the mth derivative of C is less than or equal to a constant. Have you people learned what total variation is? Did you guys study that? No, you didn't. OK. So that's important for this, for actually what comes next for both of these things. So I'll define it formally, but just think of it for the moment as the set of all functions that if I take the mth derivative and I take its absolute value, sorry, m plus first derivative, so one more derivative, and take its absolute value and integrate it, then that's less than or equal to the constant C prime. Okay, so compared to this function space, this one takes this function squared, right? M plus 1 derivatives and squares it, integrates it, and says that's my measure of complexity. This one takes the absolute value instead. So it's like the L1 analog of the Sobolev space. That's how you can think about the total variation space. Total variation, formally, let me just define it for you. I guess I'll define it down here. It's, if you give me a function, let's just call it f, its total variation is the supremum over all possible partitions. So it's the supremum over all possible partitions and number of partition points. So I'm looking at all possible partitions of the space. Maybe this function lives on, say, the space 0, the domain 0, 1. So I take all possible partitions of 0, 1. And I look at the increments of the function, absolute increments, and I add them up. That's the total variation. So it's the biggest I can make the function differ if I add up these increments in absolute value over partitions of its domain. That's the total variation. And it turns out that when f is differentiable, the total variation just ends up being equal to its derivative, its absolute derivative integrated. Okay, that's just a fact about total variation. Okay, so this you can actually see quite easily. Just compare the function f to its square. Okay, if I tell you that the integral of f squared is less than or equal to c, then because the square of a function is going to be bigger than the absolute value of a function when the function is bigger than 1, certainly that's going to mean that this is true. When the function is less than 1, then I can bound this by 1. So that's where the c plus 1 comes from. Okay, so in other words, for many years, people were doing analysis and estimation over this function space. They're saying, we have smoothing splines, we have kernels, we have RKHS estimates, we have all these things. They're optimal over this function space. Look how great life is. We can estimate these functions optimally. And then Donahoe and Johnstone came along in the 90s and said, well, actually, there are bigger function spaces. For example, here is one of them. And if you look at these function spaces, smoothing splines actually perform quite poorly outside of the Sobolev space. So they actually do very poorly here. And this function space contains these types of heterogeneous functions. So it's bigger, and it allows our functions to have spikes. They're not kind of uniformly smooth. And so Donahoe and Johnstone's theorem, let me state it for you. And then I'll explain to you the kind of two saviors, which are locally adaptive regression spline and trend filtering. So Donohoe and Johnston's theorem says that over this bigger function space, let's call it Tm of C, the optimal rate, so the best you can hope to estimate functions that live in this function space. So these can be, mixed smoothness. They can have spikes and stuff. Optimal rate is n to the minus, this is going to look a bit perplexing maybe. It's this rate, n to the minus 2m plus 2 over 2m plus 3. Okay, so that's the optimal rate of estimation over this total variation ball. Okay, the big result of Donohoe and Johnstone, they also proved that wavelets are optimal. So wavelets actually attain this rate. That automatically makes wavelets optimal over the smaller function space too. Right? That's the beauty of looking at these bigger function spaces. Wavelets work over the bigger function space, also over the smaller one. So all of the classical stuff, like Sobolev spaces, Holder spaces, they're all contained in this bigger function space. So if wavelets are optimal over this, they're also just as good as smoothing splines on the smooth problems. But here's the real shocker. But the optimal rate, let's just call it the best rate, attainable by any linear smoother is n to the minus 2m plus 1 over 2m plus 2. Okay, so these just may look like a bunch of fractional powers to you, and maybe they don't really seem like they're that interesting, but let's just take a second to look at this. Let's suppose m was 0. Okay, so looking at functions of bounded variation. This is a perfectly reasonable class. The optimal rate of estimation is n to the minus 2/3. Okay, that's achieved by wavelets. If I try to use a smoothing spline, my estimation rate would be n to the minus 1/2. Okay, it's quite a bit slower than n to the minus 2/3. What that means is that if I want to get the same error in an asymptotic sense for large data sets with a smoothing spline than I would with, say, a wavelet estimator, I would need n to the 1/6 more samples. So that's the ratio of these two rates. I need a lot more samples to get the same error. And actually, if you take the ratio of these two things, this guy is going to need infinitely more samples. The ratio diverges, goes to infinity to achieve the same error rate. So it's actually a very strong statement about how suboptimal these things are. Okay, and depending on your perspective, this could be a real dagger, right, to linear smoothers. Because, again, just to be concrete, this contains smoothing splines, regression splines, kernels, RKHS estimates, sieves, which you probably didn't learn about, running mean or running smoothers. You take simple running averages, many others, right? So basically, a very large part of the literature just does not do well for these problems of mixed degrees of smoothness. And the big result that they prove is that wavelets do well. Now, what's the problem with wavelets? Why am I even bringing up locally adaptive regression splines and trend filtering? This paper was written in 1998, so wavelets have been around for even longer than that. This is not a new result. In my experience, and this is not meant to offend anybody who works on wavelets, these just don't work well in practice. So they have these beautiful theoretical properties, but if you try to apply wavelets to even a simple problem, they actually don't work very well. And why is that? It's because they're designed for very specialized problems. So wavelets actually, in practice, they have all sorts of restrictions that they have in order for you to fit them in software. Like the function you're estimating, they say, well, is it periodic or is it cyclic? You have all these options, but maybe none of those apply. right? They also require evenly spaced points. So they require the x points to be evenly spaced. How often is that going to be in practice? So they have all sorts of restrictions that mean that when you kind of go beyond those restrictions, they just don't work very well in practice. They tend to be very sensitive to noise. So in a parallel effort, some other statisticians, Sarah Vandegeer and others, developed a version of splines that they call locally adaptive regression splines, because they're going to locally adapt the level of smoothness that are also optimal. And that's basically locally adaptive regression splines and trend filtering answer this problem both theoretically and practically. Okay, so let's just end with that. Locally adaptive regression splines. So this was 1998, maybe, around the same time as the wavelets. Like smoothing splines, they're defined by a variational infinite dimensional minimization problem. But they just use a different notion of complexity. And you could probably guess what it's going to be. So I'm going to regularize, instead of according to the L2 norm of some number of derivatives squared, the total variation. Okay? So it's like the L1 analog of a smoothing spline. So in the functional estimation world, this is like the lasso versus smoothing splines, which are like kind of like ridge regression. Okay? We're now thinking about L1 metrics. So this integrated absolute value rather than some integrated square. This is how you define locally adaptive regression splines. In the 1 minute I have left, I'm going to try to basically tell you what's good and bad about these and also tell you about trend filtering. It's very ambitious. Good is that they're optimal. Just like wavelets, they attain the optimal rate of conversions. Good, they work in practice. So they actually have very nice practical performance. Just like smoothing splines for smooth problems, so you don't lose much, but much better for problems with mixed degrees of smoothness. The bad is that they're slow. So unlike the smoothing spline variation result, there is no general result that allows us to reduce this problem to a finite dimensional form when m is bigger than 2. So actually, people have all sorts of approximations they try to do to solve this problem. Even if you fix knots to the data points, this problem is actually still pretty hard to solve. So that's the problem. They're order n cubed in practice. Compare that to the order n for smoothing splines. Trend filtering. Trend filtering came out of the applied math literature much more recently. So in the maybe late 2000s. They are basically a discretization of this problem. The double star. It's a clever approximation for this problem. Just forget about minimizing our functions. It's too hard. Let's just discretize. And what it ends up looking like is something like this. What am I going to call the? Let's call a vector of fitted values beta. So for every y, I'm going to estimate its mean by beta. Actually, let me use mu. That's probably more clear. So these are my estimates for. I'm going to solve this problem to get estimates at the points y hat. So that's just exactly this. But instead of using the total variation, trend filtering just looks at the sum of some discrete derivative operator of order m plus 1. That's just some linear function transpose mu. So in order to estimate derivatives, it just does so in a discrete sense. It looks at local differences of the parameter vector mu in order to kind of estimate derivatives. So this uses the connection that this total variation is really like the integral of the absolute value of my function, this is just a discretized version of that. That's all it is. Discretize this integral into like a Riemann sum type thing. Turns out that trend filtering basically has the same properties. It's optimal. It also works well in practice, but it doesn't have this problem anymore. The complexity of the trend filtering problem is actually n to the 1.5. Okay, so it's fast-ish. Not quite as fast as smoothing splines. And it's still good enough if you're looking at problems with mixed degrees of smoothness. Okay, so sorry that I was really rushed there at the end. I think I wanted to make sure we all understood splines well. All of this stuff is described in more detail in the notes. And you can look up papers about all this stuff if you're curious. And shoot me an email if you have any more questions. So that was it. I think Larry will probably return to his usual classification, I think it was, on Tuesday.